Welcome back to the channel, everybody. We are out here early morning and this greenhouse is warming up. It is warming up. I can shed the hat today, don't mind the hat hair. So this compost heater's pushing about 110 into our greenhouse. I can use an inset to give a nice demonstration on the amount of flow we're getting on a very, very minimal solar activity day. There is nothing coming through those clouds. But this is how winter goes. We do not have a whole lot of sunlight to run all of these systems. That's why we have such minimal draw systems. These little 3.5 watt fans that are pushing 80 plus cubic feet per minute are really pushing a lot of heat around. As you can see, I have my stove going. I've got myself some pine needle tea in there, got our little fan. We've got some sand experiments, but today we are out here talking about compost heating and heating your home with natural gas, and we are going to compare the two, and we're going to compare the cost of heating your home to the cost of doing this, I suppose, and then the actual BTU outputs, and then we're going to do the emissions on both of them, how much they actually emit of CO2 back into the atmosphere. Now, if that sounds interesting to you, please consider subscribing to the channel, because that's pretty much all we do is nerdy science stuff in the greenhouse. Before we get started, I want to kind of run around the greenhouse and just show everybody what we've got going on here. We've got a whole lot of moving parts all the time, and I'm always working on stuff that kind of gets looked over. I really like to show everybody bits and pieces as opposed to just showing a brand new product like bam, here it is. So we show little bits and pieces of everything. So let's go. So first of all, starting down at the stove, we've got all of these systems running just to push a bunch of heat through down to the other end of the greenhouse, and I have another fan running down there. So I ended up having a little bit of extra sand, and we are putting this up here, and we can kind of check and see here. So this sand, well, the sand is going to be about 160. Whew. So right here, so I picked up a couple 5-gallon buckets of sand for free that I was able to reuse in a whole bunch of these little containers, and I'm reusing for a whole bunch of different things. So this thing right now is still holding about 110 degrees on one side of it. So this is going to release a whole bunch of energy. I got this little container that I had to develop some type of reservoir, kind of like if you think about a coolant system for your car. They have an overflow tank, and you have to have some expansion tank for heating and contracting and extra fluids to fill your system. So you can see this little guy here. I mean, you can hear this little guy. We got this little dial here, and this is AC or DC. I can run this off solar power. I know I've got it plugged in. We've got a nice cover. It is not using a whole lot of juice, so I'm able to use this. This is not the best transfer device for this. This is an experiment that is coming down the pipe here, but it's only blowing through like a little sliver right here, about a 4-inch square by 1-inch square, but it really moves that air around, and it's just experimental. All of this is experimental. I just wanted to give a little teaser here and explain why I'm using this. This thing is really drawing some air through here, this blower, and it is cranking air down, thus exchanging it back and forth with the greenhouse at a lower level, and it's really aerating this tunnel and giving some good oxygen flow there. So this is something I've been working on in the back burner for the last like month or so, and we've got this little sandbox here that is going to be powering it. Lots of little cool things that are going to be coming down the pipe, and I've got this heading collards that I've just kept in this bubble water. It was compost tea water. I've been in here for a day or two, so they're about ready to get planted out into the greenhouse here. Everything looks awesome. We had pulled up our potatoes, got some residual onions left over here, but for the most part everything looks good. We've been using a whole bunch of rocks we're digging up. Got tons of rosemary planted in there as a natural pest barrier. Lots and lots of stuff. Just wanted to kind of give a highlight of the greenhouse, all the perennial stuff sitting, a bunch of elderberries, a bunch of free sand, and this is another idea. You can fill a whole bunch of wine bottles with sand if you can dry the sand out and easily pour it in. Other than that, we got a whole bunch of pickle jars that we're going to be able to continue to reuse. This little mini cold frame that I've built out of just recycled windows has made its way around the greenhouse, and this is a perfect example of what I can use a hot jar of sand for. So we could heat this up to 150 degrees, stick it inside here, put more windows or a piece of insulation on it, and then you have a nice hot steamy little greenhouse that even if you don't have any sun, you can actually heat this up. You can run your compost heat right to a little greenhouse like this. Just want to show this real quick. We use these windows, laid them flat here, and we've got a ton of plants growing underneath all of those. Very cool little cold frame use here, and we've got a window on the back side to block anything else out. So the only side that's open is the side facing the walkway, so the inside of the greenhouse, the warmest part. So these sandbags catch some heat. Very cool to be able to reuse all these little windows. I already knew this video was going to be a long one, so I figured I might as well just give an update on everything going on as we've got our compost heater running. So you can see how this is just slowly pulsing. You can see when it's hitting, it starts to break it up, and then it's just running. So we're pulsing that 110, maybe 108 degree air, just slowly pulsing through that fan. Just every 15 seconds it's pulsing because we have absolute no sun right now. These bricks have 100 degrees. About 70 degrees on the outside here. We've got that fan just like this fan blowing through, and this sucker is just cranking about 160, 170 all the way around the greenhouse, moving some seriously good heat. Along with this Peltier device fan, it just runs, turns heat to electricity. This geothermal is running off the same solar power system as all of the fans over here. We are just slowly pulsing that air. It'll rise on its own and then it gets blown. So we're slowly pulsing that air over all of these beds into the greenhouse and keeping a constant 50 even when there's no sun or any other heat source. So I believe that that is all of the updates from the greenhouse. Everything looks really good in here. Just coming down to get a heading collard snack. Look how clean this plant is. Just absolutely beautiful. No bugs, no nothing. So I'm going to go ahead and I'm going to wash my coffee cup out real quick. I always bring a jug of water from the house so I can clean things up. That's why I got this recycled sink here. I really like having it. Everything I rinse out. And then we just take this bucket full of water, whatever we rinse out, and if it's not food or anything, we can just water the greenhouse with it. And we really don't have any chemicals, no soap or other than regular goat soap. So there's no actual chemicals in the greenhouse here. So it's very cool to be able to have that little sink. I got it covered up right now. I have a whole bunch of fodder starting on there, a whole bunch of sprouts of a soft wheat berry, a soft white wheat berry. So we've got a ton growing. We can eat that ourselves, give it to our chickens or any animals. I'm gonna go ahead and I'm gonna pour myself up some pine needle tea here. This pine needle tea is very high in vitamin C, and it's just all around good for you. I guess I'll give you guys a better background here of the entire greenhouse. So as we're breaking down all of these numbers, I want to talk about this. I met a farmer at the farmer's market selling stuff just like us. He had very early tomatoes. I asked him about it, and he said he got a grant to get a huge greenhouse built, or a big greenhouse, probably twice the size of ours, and then he put a huge furnace in it to put natural gas. Actually, he has an LP tank or a propane tank like us, so we're out in the country far enough we don't have natural gas ran, so we're stuck using an LP tank. I know how much that costs. It's like 600 bucks or whatever, plus he filled that up 3 times, and that will relate to about $1,500 to $1,800 depending on the cost of fuel at that time. That is a lot of money. That's more money than we spent on this whole greenhouse. We have all of everything you see inside the greenhouse plus some invested into $1,800. And not to mention that was only heating it for maybe 2, 3, possibly 3.5, 4 months at the most. So that's a lot of money invested. You're gonna have to sell a ton of stuff, ton of produce to be able to recoup those losses. So the average cost of natural gas per therm in my area is about 38 to 40 cents per therm, which is relatively low. If you look at Los Angeles, California, you're going to be paying about $1.69 per therm, and 1 therm is just 100,000 BTUs. What is a BTU? It is a unit used to measure the capacity of heat that a fuel source will hold. It requires 1 BTU BTU to heat 1 pound of water 1 degree Fahrenheit, and it requires 0.24 BTU to heat 1 pound of air 1 degree Fahrenheit. 1 pound of air is about 13.33 cubic feet of air, to give you a reference of space. Just to give you a quick example, a 1,000 square foot home is going to have about 9,000 cubic feet if you have 9-foot ceilings. So that's how much cubic feet you have to heat. Now some more food for thought here real quick. Zone 6 and up are paying 30 to 35, maybe 40 BTUs per square foot to heat their home. And if you're living in 5 or lower, 5 to zone 1, you're going to be paying 30, 40, 50, even 60 BTUs per square foot of home just to heat that. Now there's a lot of variables to that, but that's just to give everybody a basic understanding of what we're talking about today. So your average household furnace is going to be about 60,000 BTUs. Hopefully I can get all the numbers on my screen to work properly today, because I have a lot of numbers coming. So I'm going to be showing all my numbers hopefully right up here. So average home is 60,000 BTUs to about 100,000 BTUs. And that goes from 1,000 square foot up to 4,000 square feet. So there's a lot of variables in that, but that's rough estimates. Now for the sake of this exercise, we're going to say that your household furnace is 100% efficient, and they are not, let me tell you. So getting 97% efficiency would be immaculate. That would be amazing. So most of them are between 80 and 90%, 90 being a high efficiency furnace. So you're going to get 80% of your heat going to your home, 20% is lost. A high efficiency 90% is heated your home, and 10% is lost. So on average, they're going to run for 8 to 9 hours a day. That is because they're going to run for 10 to 15 minute intervals, running for possibly 20 to 45 minutes per hour. So basing that, we're going to say it's running about 8 hours a day, maybe 9. So based off that, we're going to take 8 and multiply it times 60,000, because it ran 8 hours in a 24-hour cycle, and we've got 480,000 BTUs used in one day. Multiply that by 30 for an average of 30 days in 1 month. You're going to use 14.4 million BTUs in 1 month just to heat that 1,000 square foot home with a 60,000 BTU per hour furnace. So we take 14.4 million divided by 100,000, which is 1 therm, to 100,000 BTUs. So we're trying to find the therm. So we're going to find 144 therms per month. So that person in California paying $1.69 is going to have a bill of around $243 a month, plus delivery and tax. So that is crazy. If we were paying for our 40 cents per therm, it's about $57. That's quite drastic. That is without tax or delivery. Deliveries sometimes can be as much as the actual bill itself. Now that is based off 100% efficiency, no taxes, no delivery included, just basic numbers for everybody to help everybody understand what we're talking about. So we'll come back to gas emissions after we talk about our compost and the amount of heat we're able to produce with compost. So on average, per cubic yard of active compost, you're going to get about 1,660 BTUs per hour, and that's while it's active. So let's take that up to 1 ton, which is 4 cubic yards, giving you about 6,600 some BTUs per hour of compost being active. Scaling that up once again to the 9 tons that we have in our compost pile, we are able to produce about 59,000 BTUs, and that is just shy of the 60,000 BTU furnace it requires to heat a home. Now also, I am going to share numbers from our 9-ton pile and Jean Payne's 50-ton pile of compost or wood chips like us. So we're going to say that even if we have 8 hours of sunlight, we might get 9 hours of heating in the greenhouse with all of our solar power and our Jean Payne systems together, possibly doing a thermophilic draw, basing it off a 9-hour cycle of heating per day. So with 9 tons creating 59,000 BTUs, we're going to say that is times 9 hours a day, pretty darn close to the 480,000 BTUs per day that natural gas produces. And that breaks us down to about 14.3 million BTUs used in a 30-day cycle, and that is going to give you a therm of 143 therm. If we were relating that to gas cost and you heated your home in Los Angeles again for $1.69 a therm, that would be a $241 bill that we are not paying for 6 months to a year at a time with all of this free heat. Now let's jump over to John Payne himself's compost heater, his 50-ton compost pile. Now 50 tons is going to create about 332,000 BTUs per per hour. That is just an astonishing number. We're going to base that off of a 9-hour heating day, just like us, 9 hours of heating cycle with solar powered timing systems, etc. We're just going to do them the same for the sake of this experiment. It's going to create about 2.988 million BTUs per day. And over a month span, Jean Pain was creating about 89 point some million BTUs per month, and that is just crazy amount of heat. So let's relate that to having a $1.69 per therm. He had himself about 896 therms times $1.69 heating in California. That is going to be about $1,500 for a heating bill if you were trying to produce or recreate the amount of heat from his compost pile with natural gas. That is very cool and interesting stuff. I like to share the data from that. And let's switch gears from heating to emissions and see what kind of emissions both of these heating sources produce. So 1 ton of compost is going to produce about 160 kilograms of CO2 per its life cycle. Before I relate that to our 9-ton pile, I want to break down 1 kilogram or about 2.2 pounds of CO2 equals about 20 cubic feet of CO2, taking up 20 cubic feet of space. So relating those numbers, your 1-ton pile is going to produce about 3,100 cubic feet of CO2 per life cycle. Just a quick comparison, a cow releases about 6,000 liters of CO2 or about 211 cubic feet of CO2 per day. I am not going to measure the methane or the nitrous or anything else that is coming off of our compost pile because it's hot, so it's kind of venting all of that slowly, and it does produce some of it. So I could get technical in another video and show every potential hazard that comes off of a compost pile, but I feel like they're so minimal that if I don't have the pile inside the greenhouse, I don't have to worry about those numbers, and it's really not that bad of an emission. Methane is not good for our planet, but methane is created in the absence of oxygen. So if there's plenty of oxygen trapped up in those wood chips, we will have a long burn that doesn't create a whole lot of methane, and methane is produced at about body temperature. So if we're above body temperature, it's not creating a whole lot of methane. So now that we know how many CO2 emissions come off of our compost per cycle, per year, or however long it burns, so it takes a little converting here. Natural gas produces about 55.8 grams of CO2 per megajoule. 1 megajoule is 1 million joules, or only 948 BTU. So it's really not a large measurement. So therefore, every 948 BTUs, we are producing 55.8 grams of CO2. And that 55.8 grams of CO2 is actually 1 cubic foot. That is the measurement of 1 cubic foot of CO2. So let's divide our 60,000 BTU per hour by 948 BTU. We get about 63 cubic feet of CO2 produced per 1 hour of use. And we get 63 cubic feet of CO2, or 3,515 CO2 grams per megajoule. Now, just in one day, that 60,000 BTU furnace is producing 567 cubic feet of CO2 out into the atmosphere, 2 times the amount of 1 cow. Now in 1 month's time, we're producing between 17 and 18,000 cubic feet of CO2 into the atmosphere. And after a 6-month period, we're producing 102,000 plus cubic feet of CO2 into the atmosphere. So somewhere around the 1.5-2 month mark, we are leveling off with our compost production of CO2 to the actual natural gas production of CO2. So I can say that in a year's time of heating with compost, this will still be warm in the summer if we need heat in the summertime. In 1 year's time, we're going to produce 205,000 cubic feet of CO2 into the atmosphere using a natural gas furnace, as opposed to that compost heater, which has a finite amount of carbon and resources, and it's only going to release X amount. And this compost is absolutely pertinent for our homestead. We are trying to do a permaculture nursery. We're going to build more greenhouses. We are really trying to get the ball rolling here, and this YouTube sharing is very much helping us out. We are getting a lot of our information out there, getting a lot of great feedback from all of you guys. Our subscribers are absolutely awesome with your ideas and stuff. And back to all the nutrients that are for free coming from that compost. These break down for a year year cycle, 7, 8 to 10 months to a year, and we have all of those free resources. We've got 9 tons. That may break down to 7.5 to 8 tons of usable material once this is all done burning, but we're able to use that on our homestead. We're able to use it as nursery stuff, free compost. We're just spreading it everywhere, adding humus, adding life to the whole property, and that is just what it's about. Reusing that complete heater. All of the systems, we barely spent anything on this heater this winter. I used systems I had, I used some extra tubing I had. Everything was already in place. All I had to do was plug it in and drop the pile, get it hot. So before this video gets too long and boring, I'd like to thank everybody for watching. Just try to put all this in basic terms so everybody could understand, hopefully, and it's not too much jumbled material or info coming at one time. So if there's any questions or discussions, you know where to drop them, and I will see you guys next time.